Good morning, Nathan. Welcome to lecture number 1 on differential calculus. My name is Charles. The presentation outline will look as follows. We'll briefly talk about differentiation, then we'll look at differentiation of a constant, a variable, cosine and sine function, then we'll move on to look at derivative of natural logarithm functions as well as exponential functions. And in each of these, we'll be giving examples, and then finally we'll look at the standard differentials. I'll also give a reference text, which I feel is very critical in the understanding of this presentation. Now, differentiation is used in calculations involving velocity and calculation, and the acceleration rather. It's basically a method of determining rate of change of a given function, and is mainly used to determine also maximum as well as minimum values of a curve. So in the next examples, we'll be basically looking at how to find the differentiation of a constant, a variable, cosine and sine function, natural logs as well as exponential functions. Let's begin with the differentiation of a constant. Given any constant y equals 23 or t equals 100, the derivative of any of these constants will always be equal to 0. A 0 here signifies a 0 rate of change. And so it doesn't matter the value of that constant. It could be positive or negative. Every time we differentiate a constant, take note it will always be equal to 0. Next, let's look at derivative of a variable. A variable could be any function of y. In this case, you may have y equals ax to the power n, or you may have f of x equals ax to the power n. Each of these functions are basically variables. It means that y is changing with respect to x. So the values of a will be changing depending on the value of x, and therefore they are called variables. To find the derivative of any function y equals ax to the power n, this will always be equal to a scenario whereby you have the function ax to the power n. So for a function y equals ax to the power n, to find the derivative dy over dx, you simply get the power n here, multiply it by the coefficient a, and this coefficient a basically gives you an multiplied by x, and then the same power n subtract 1, basically n minus 1. You do the same for any function of x equals ax to the power n. So therefore, the power multiplies with the coefficient, and then this power again is subtracted by 1. So let's look at an example to illustrate this. In terms of an example, so if you have 3 examples here, A, B, and C, let's look at the first example where, example A, where y is equal to 5x to the power 7. So in this example, you have a function y which varies with a variable x, and this x has a power of 7 with a coefficient of 5. To find the rate of change of this function, rate of change basically dy over dx, rate of change of y with respect to x, we take the power 7 multiplied by the coefficient 5, giving us 35, and then on the power 7 we subtract 1, that gives us 6. Therefore, the rate of change of the function y equals 5x to the power 7, basically dy over dx, end up being 35x to the power 6. We can move on to example number 2. In this case, example number B, you have y equals 3 to the power 3 multiplied by root of x. Now 3 multiplied by root of x. This root here can be simplified as x to the power half. Therefore, x will now have a power of half, which is basically a root. Then this root can be multiplied again by the coefficient 3. So this coefficient of constant 3, when you multiply it by half, you have basically this part. And then the power half will be subtracted by 1, giving us minus half in this case. And simplifying this, giving us the final answer, which is simply 3 divided by 2 multiplied by the root of x. And then we can move on to the next example, where we are now looking at example number 3, y equals 4 over x squared. In this example, y equals 4 over x squared can be written as 4x to the power minus 2, where the denominator x squared changes to x to the power minus 2 when it is multiplied by 4. And in this case, the power then changes to minus 2, while the coefficient 4 remains, which is a equals 4. Therefore, to find the rate of change of y with respect to x, again, the power multiplied by the coefficient an x to the power minus x to the power n minus 1, which simply means, again, you can actually take the 4 there, which is your a, multiplied by the power, and then the n, which is minus 2 minus 1. This part now reduces to basically minus 3. And then 4 times negative 2, you have minus 8. And then multiplied by x, which is then simplified to give 8 over x to the power 3 as a negative answer. We can try now another example which involves more than one variable. In this case, we may have y equals minus 2x squared, which is the first term, plus the second term 3x minus 12, which is a constant here, and the third term. And to differentiate y with respect to x, we do it term by term. So beginning with the first term here, this is, you're going to multiply 2 by minus 2, giving us minus 4 in this case. And then 2 minus 1 in this case, we are going to get x to the power 1, or simply x, which is what we have here in the first term. Then moving on to the second term, 3x here, there is a silent power of 1 there. So 1 times 3, giving us the 3 here. And then this same power minus 1, this gives us x to the power 0 in this part, and any number to the power 0 gives us a 1. Therefore, 1 times 3 just giving us a 3 here. When it comes to the third term here, which is minus 12, you know, the derivative of any constant like we saw earlier, this will always give us, it will always give us a 0. Therefore, the final answer for the derivative of y, dy over dx of this function will simply be this answer, which is given here. Let's move on now to look at the next set of derivatives, how to differentiate a sine and cosine functions. Now, given a sine function y equals sine a theta, where theta is an angle, in this case, we can find the derivative dy over theta, or the rate of change of y with respect to that angle theta, as simply for a sine, you get a cos a theta, and then again this you first of all bring the coefficient a here, and then find the derivative of sine, which is basically cos a theta. If you're given a function y equals cos a theta, again, bring the coefficient before the cos, which is what we have here, and then find the derivative of cos a theta, which is minus sine a theta, where a, again, is a constant in this case. So let's do an example to illustrate this rule. We have two examples, A and B, where A is you have y equals 2 sine 5 theta. In this example, you notice that theta here represents an angle. This 5 here is a constant. Then you have this part here, which is a coefficient. That's a coefficient. And then this one is 5 is a constant. Therefore, what you do is to find the rate of change of y with respect to this angle theta, bring the 5, let the 5 be multiplied by the coefficient. Therefore, we're going to have 2 multiplied by 5, which is 10 here. And then derivative of sine 5 theta is simply cos 5 theta. Therefore, final answer is 10 cos 5 theta being the derivative of y equals 2 sine 5 theta. In the second example, we can do a similar thing. Given a function of t, f of t equals 3 cos 2t. To find the derivative, first of all, move that constant, b multiplied by that coefficient, and that is what you have here. You're going to get a 6. Then the derivative of a cos is minus, that's a minus you're seeing here, and then you simply write the 2t there. Therefore, the final answer simply becomes minus 6 and 2t as the derivative of 3 cos 2t. Okay, so let's move on to the next next set of functions. Let's move on to the next set of functions. We have where we'll be looking at the differentiation of exponential function as well as natural logarithm function. So if you are given an exponential function as given an exponential function y equals e to the power ex, we can find the rate of change of y with respect to x, which is dy over dx, as simply e to the power x. But it may also be shown that if y is equal to e to the power ax, where you have now a constant there a, the rate of change of y with respect to x dy over dx will simply be get this constant, bring it here, which is what you have here, and then you replicate the same function as it has been given in y. So that becomes the rate of change of y with respect to x dy over dx. Then coming to logarithm function, if we are given a natural logarithm function y equals in x, then dy over dx will simply be 1 over x. And in some cases, you may have a constant for x there. The rate of change of y with respect to x will still be 1 over x, irrespective of the value of a there. So let's do some examples on this one. In doing some examples, let's have these two examples to do with exponential functions. Given the first exponential function in example A, y equals 3e to the power 2x, you will notice that in this function here, it has two parts. It has a coefficient 3 here. It has a constant of x, the constant of the variable x, 2 here. Therefore, the first thing is to multiply the constant and the coefficient as we calculate the derivative of y with respect to x. And when you multiply 2 by 3, which is given in this case, then the rest of the function remains as it is here. Okay, so this gives us a 6 e to the power 2x. If we looking at example number 2, if you are given a function f of t equals 4 over 3 e to the power 5t, the first thing to do is to basically write this as a product. So this can be written as 4 over 3, then the exponent, when it goes above the division sign, then the power of the exponent becomes negative, as you can see here. And then we can now apply the rule where this constant, the whole lot of minus 5, being multiplied by 4 over 3, which is what is illustrated here. And once we multiply these two, we get minus 20 over 3 exponent minus 5t, which basically can also be written as minus 20 divided by 3 e to the power positive 5t, just if we change this into a positive. So let's move on to look at another example now involving the natural logarithm functions. You notice that given a natural logarithm function y equals 5 over 5 in 3x, this can actually, be written as, this can be written in terms of y equals 5 in 5x, which is what we have here. And in this case, this constant has no bearing in the derivative. So if we take the first, this part of the function, then 3x is simply 1 over x. 1 over x multiplied by that 5 here, which is this one here, and then this becomes 5 over x as our final answer. Yeah, so we also have standard derivatives, and from the standard derivatives, you can see that ax to the power n, this can be derived as ax to the power n minus 1, and the derivative of a sine ax function is a cos ax, while the derivative of cos ax would be minus a sine ax. For exponential and logarithm function, the derivative of e to the power ax will always be ae ax. Well, in ax will always be 1 over x. So this marks the end of our presentation. Take note of this reference book.